Hello, my name is Judah Rosno, and this is my report for Case Study 6. Our objective was to evaluate the numerical integrity of an off-the-shelf stainless steel mending plate acting as a strain release strap and a knee brace. Our main concern was whether the stress concentrations around the holes would cause fatigue failure. Per our constraints, we must make a data-driven recommendation immediately, relying purely on computational theoretical verification as no physical validation data exists. I modeled the plate using AISI 304 stainless steel and constrained it to the attachment points. I used roller sliders on the sides and the back. I wanted the part to be able to buckle outwardly away from the leg if that occurred. To accurately model the 687.7 Newton compressive load occurring in the stair descent, I utilized a bearing load rather than a standard uniform force. A bearing load is crucial here because it realistically simulates the non-uniform parabolic force transferred directly from the bolt to the cylindrical face of the brace's hole. For the mesh, I utilized solid high-order tetrahedral elements. Initially, the thin walls of the plate had only one tetrahedral element of thickness, which is mathematically insufficient for capturing accurate bending stresses or internal strain gradients. To resolve this efficiently, I implemented an H-adaptive mesh refinement study. After 4 loops, the mesh converged, successfully dropping our total relative strain engine norm error below 1.43%. Static simulation showed a maximum von Mises stress of roughly 134 megapascals, which is more than the yield strength and gives us a factor of safety of roughly 6. The fatigue factor of safety plot within SOLIDWORKS returned a factor of safety greater than 3.3, as well as a load factor much greater than 1. Because cyclical loading is our primary concern, I verified the model's numerical integrity using hand calculations. Utilizing Peterson's stress concentration factors for a finite width plate with a hole, I determined a fatigue notch factor of 1.94. I then applied the modified Goodman criterion, yielding a calculated endurance limit of 205.91 megapascals. Comparing this against our simulated stresses gives us a theoretical fatigue factor of safety of 3.6. Our target threshold was a factor of safety above 2.0. Because 3.65 comfortably exceeds this requirement, my recommendation based solely on data is to proceed with the off-the-shelf component. However, validation is necessary before mass production, but based off data, it will safely survive the fatigue loading without requiring a custom redesign, saving both time and manufacturing costs. Thank you.